Welcome to Late Night History. Settle in wherever you are. Let your shoulders drop away from your ears, let the phone rest a little lower in your hand, or set it down entirely, because you will not need to look at anything tonight. There is nothing to watch. There is only a voice, and a place, and a long, slow walk down into the quiet strangeness of the world we happen to live on. You can close your eyes now if you like. Nothing important will happen suddenly. Nothing will jump out at you. The story tonight moves at the speed of deep water, and it is meant to carry you down gently, the way a tide draws back from a shore in the dark, patient and unhurried, and sure of where it is going. So let me begin with something that is almost impossible to believe, and yet is completely, measurably true. Somewhere in the Indian Ocean, south of the tip of India, out past Sri Lanka, where the sea opens up into that enormous blue emptiness that goes on and on toward Antarctica, there is a place where the ocean is missing. Not missing in the way a lake dries up, not missing in the way a river runs low in summer. The water is all still there, ships still cross it, fish still move through it. But the surface of the sea in that place sits lower than it has any right to. Lower by more than 100 meters. More than 100 meters of ocean, in a sense simply gone, sagging down into a vast shallow bowl that spreads across something like 3 million square kilometres of the planet's face. Let that number rest in your mind for a moment, softly, the way you would set a stone down on a table without a sound. 3 million square kilometres. That is a stretch of ocean larger than many whole countries, larger than a great many nations you could name, a dent in the sea wider than the distance you could drive in days. And in the deepest part of that bowl, the surface of the water lies roughly 106 meters below where it ought to be. 106 meters, taller than most buildings you have ever stood beside. And the sea has quietly slumped that far down, across an area you could not cross in a lifetime of walking, and here is the part that undoes people when they first hear it. No one has ever seen it. Not one sailor, in all the long centuries that human beings have crossed that ocean, has ever looked out over the rail and noticed anything at all. No ship has tilted, no compass has spun, no wave has behaved strangely. You could sail directly across the very lowest point of this 100-meter depression, back and forth, all day and all night, for the rest of your life. And you would feel absolutely nothing. The water beneath your hull would look exactly like water. The horizon would sit exactly where a horizon always sits. And this is the first thing I want to unfold for you tonight, slowly, because it is the thing that most people get wrong. And getting it wrong turns a gentle wonder into a frightening rumour, and there is nothing frightening here at all. There is no hole in the ocean. Let me say that again, because it matters, and because it is the kind of sentence you can drift off, holding on to without any unease. There is no hole. There is no pit, no whirlpool, no great dark chasm in the water that a ship could tumble into. If you imagine a giant crater scooped out of the sea, a wall of water you could stand at the edge of and peer down into, then let that picture go, gently, like letting go of a balloon string, because that picture is simply not true. The reason no one can see this enormous dip is that it is spread out over such a colossal distance that the slope of it is far too gentle to notice. Picture it this way. Imagine you are standing on a football field and I tell you that one end of that field is a single millimetre lower than the other. You would never see it. You could not see it. Your eye has no way to detect a slope that's slight over that much ground. Now stretch that idea across thousands of kilometres of ocean. The sea surface does drop, really and truly, by more than 100 meters from the edges of the bowl down to its center. But it does that over such an immense width that at any single spot, at any place a ship actually sits, the water looks perfectly flat. Because it is, for all practical purposes, perfectly flat right there beneath you. The bowl is real. It is just so wide and so shallow in its grade that the human eye and the human body and every instrument a sailor ever carried on deck all pass right over it without the faintest signal that anything is unusual at all. So it is not a hole in the water. It is something stranger and quieter than that. It is a dent in gravity itself. And this is where the story begins to open up, so let me take you into it carefully. Over that patch of the Indian Ocean, gravity is a little weaker than it is almost anywhere else on the surface of the Earth. Not weak enough to notice. Not weak enough that you would float or feel light on your feet, or watch a dropped cup fall in slow motion. Nothing so dramatic. But weaker in a way that can be measured with exquisite precision, weaker in a way that is, in fact, the single largest weakness of its kind anywhere on the entire planet. If you could stand a set of impossibly sensitive scales out there on the water, you would weigh very, very slightly less than you would over almost any other ocean on Earth, a vanishingly small difference, far too small for you to ever feel in your own body. But real as your own weight in a doorway right now. And that faint, unfeelable weakness in gravity is exactly why the sea surface sags. Because here is the quiet secret that the whole of tonight's story turns on. And I will unfold it for you as slowly as I can, so it settles rather than startles. Water does not simply lie flat because someone decided it should. Water responds to gravity. Water is pulled. And where gravity pulls a little harder, water gathers and heaps up ever so slightly, drawn in like iron filings leaning toward a magnet. And where gravity pulls a little more gently, the water is not held as tightly, and it eases away. It slumps, it settles lower, the way your body sinks a little deeper into a mattress in the places where it is not being held up. The sea over the Indian Ocean sits low because gravity there is not tugging on it quite as firmly as it does elsewhere. The ocean is simply obeying. It is doing exactly what water always does. It is following, faithfully and silently, the shape of the pull beneath it. This place has a name, and I will give it to you now, because we are going to walk through it together for a long while tonight. It is called the Indian Ocean Geoid Low. The Indian Ocean Geoid Low. Sometimes people shorten it to the Geoid Low, or simply the Low. And I may do the same as the hours go on, so that the words themselves grow soft and familiar, and stop feeling like anything you have to concentrate on. The Low. A place where the sea leans down because gravity has grown faint, and no one on the surface will ever know. Before we go deeper, let me do one small, warm thing. The way you might glance around a quiet room to see who else is awake at this hour. Wherever you are listening from tonight, whatever country, whatever city, whatever small dark room with the light turned low, I would genuinely like to know. If at some point you feel like leaving a word to say where in the world you are, the comments are there, and I do read them. There is something steadying about it, the thought of all of us scattered across the surface of this same strange planet, some of you over that very ocean perhaps, all of us drifting towards sleep at the same slow speed. And if this is your first night here, and you would like more of these quiet journeys into the deep and half-forgotten corners of the world, you can subscribe, and the next one will find you when you need it. That is all. No hurry. We will not mention it again. Because tonight I want to do something unhurried and a little unusual. I want to follow this emptiness downward. I want to start up here, at the surface of the sea, where nothing seems wrong at all, and I want to sink slowly with you through the water, and then through the floor of the ocean, and then down into the rock beneath it. Down and down through hundreds and then thousands of kilometres of the planet's dark interior, until we reach the thing that is actually missing, the thing that reaches all the way up from 1,000 kilometres below the waves to press this faint, invisible dent into the top of the sea. And along the way I want to answer the questions that ought to be forming, softly, at the back of your mind, even as you begin to drift. Because the first of them is a real puzzle, and I will leave it hanging gently over us like a lamp left on in the hall. If this dent cannot be seen, if no sailor ever felt it, if no eye could ever catch it, then how on earth did anyone ever find it at all? How do you discover a thing that hides from every sense you have? Hold that question loosely. We will come to the man in the submarine before long, and the swinging pendulum, and the twin satellites chasing each other around the planet in the cold and the dark. But not yet. First I want you to understand, really understand, in a calm and grounded way, what this thing even is. Because to know how we found the low, you first have to know what shape the Earth is actually pulling the ocean into, and it is not the shape you were taught. So let us talk about the true face of the Earth, and let me undo, very gently, a picture you have almost certainly carried since childhood. You were taught that the Earth is a sphere, a ball, a blue marble hanging in space, round and smooth and perfect. And that picture is close enough for most purposes, and it is a lovely picture, so keep it if you like. But it is not quite right. The Earth is not a perfect sphere. It spins, and the spinning flings its middle outward, just slightly, the way a spinning lump of dough would bulge at its equator, so the planet is a little wider around its waist than it is from pole to pole. That fatter, squashed shape has a name. Scientists call it the reference ellipsoid. And I want you to hold on to that phrase, softly, because it is the idealized, smoothed out, mathematically perfect version of the Earth that everything else gets measured against. The reference ellipsoid is the Earth of the imagination. It is the flawless, gently squashed ball that the planet would be if it were made of something perfectly even, if every part of it had exactly the same amount of stuff packed underneath, if there were no mountains and no ocean trenches and, more importantly, no lumps or gaps hidden deep inside. It is the Earth as a smooth idea, a reference, a standard to hold everything up against. But the real Earth is not smooth on the inside. The real Earth is a thing of extraordinary unevenness, packed with denser regions here and lighter regions there, with vast slabs of heavy rock in one place and lighter, warmer material rising in another, all of it buried far below where any of us will ever go. And because gravity depends on mass, on how much stuff is gathered in one spot, the pull of the Earth is not perfectly even across its surface. In some places, where there is more mass concentrated below, gravity tugs a fraction harder. In other places, where there is a shortage of mass down deep, gravity tugs a fraction more gently. And the ocean, faithful as ever, responds to all of it, heaping up over the strong places and sinking down over the weak ones. If you could take away the tides, and take away the winds, and take away the currents and the storms and everything else that ruffles the sea, and let the water go perfectly still, and imagine that the ocean wrapped all the way around the entire globe, over the continents and everything, covering the whole planet in a single quiet skin of water that answered to nothing but gravity and the spin of the Earth. Then that water would settle into a very particular shape, a lumpy, uneven, gently rolling shape, high in some places and low in others, tracing out exactly where the pull is strong and where the pull is faint. And that shape, that imaginary still surface of a global ocean obeying only gravity, has a name too. It is called the geoid. The geoid. Sit with the word for a moment. It sounds technical, and it is a real scientific term, but the idea underneath it is soft and almost beautiful once you see it. The geoid is the sea level of gravity. It is the shape the water makes when it listens only to the pull of the Earth and to nothing else. It is the truest possible answer to the simple-sounding question, where, really, is sea level? Because sea level is not one smooth height wrapped evenly around the globe, the way we imagine it. Sea level itself rises and falls, gently from place to place, following the hidden lumps of mass below. The geoid is the map of that. It is where the ocean would rest if it could rest completely, drawn into every high and every low by the uneven weight of the world beneath it. And when scientists measure the geoid, when they carefully map out where that gravity-level sea surface actually sits, and then compare it against that smooth imaginary reference ellipsoid, against the perfect squashed ball the Earth would be, if it were even all the way through, they find that the two do not match. They do not match anywhere, in fact. Everywhere you look, the real geoid is either a little higher than the smooth ideal or a little lower, and the amount by which it differs, up or down, from that perfect reference shape has its own name, one more soft technical phrase to let settle over you like a blanket. It is called geoid undulation. Undulation, the gentle rising and falling, the swell and the sag of the true surface of gravity against the smooth pretend Earth we measure it against. Now here is where it becomes wonderful and a little dizzying in the good and drowsy way. If you were to take the whole Earth and paint onto it not its coastlines and its countries, but only its geoid undulation, only the highs and lows of gravity, only the swelling and sagging of that still imaginary sea, you would get something that looks almost nothing like the neat round planet you know. You would get a lumpy, bulging, dimpled thing, a shape so irregular and so far from a smooth ball that the people who study it have a nickname for it, an affectionate, slightly silly nickname that I love, because it takes something vast and humbling and makes it cozy. They call it the potato, the gravity potato, the geoid potato. Because when you draw the Earth by its gravity instead of by its geography, and you exaggerate the highs and lows so the eye can see them, the planet stops looking like a marble and starts looking like an old lumpy potato pulled up out of the ground, swollen here, pinched there, dented over in one place and bulging out in another. And the swellings and the dents on that potato are not small ideas dressed up in big words. They are genuine, measurable rises and falls in where the ocean sits. In some places the geoid bulges upward, and the sea rests higher than the smooth ideal, drawn up by extra mass below. There is a great gravity high, for instance, out near New Guinea and the Western Pacific, and another rise up near Iceland in the cold northern water, places where the geoid climbs to something like 85 metres above the smooth reference ball. 85 metres of the sea heap gently upward, invisibly, because gravity there is pulling that little bit harder. And then, on the other side of that same lumpy potato, there are the dents, the places where the geoid sags down below the ideal, where the sea slumps because the pull has gone faint. And of all the dents on the entire surface of the planet, across every ocean and every hidden basin, there is one that goes deeper than any other. One low that drops further below the smooth reference Earth than any other low anywhere in the world. And you already know where it is, because we began there tonight. It is the Dent south of India. It is the Indian Ocean Geoid Low. And it reaches down to roughly 106 meters below the smooth ideal Earth. 106 meters of missing sea surface, the single deepest dimple on the whole gravity potato. So think of the range of it, softly, as you lie there. From the highest high, that gentle 85-meter swelling out by New Guinea, down to the lowest low, that 106-meter sag in the Indian Ocean, the entire surface of gravity across the whole planet rises and falls through something like 190 meters. 190 meters from the top of the highest gravity swell to the bottom of the deepest gravity dent. That is the full undulation of the geoid. That is how much the true sea level of the world wanders up and down as it traces the hidden weight of the Earth beneath it. And our low, the one we are following down tonight, sits at the very bottom of all of it, the deepest point on the whole potato, the place where the planet's pull has grown fainter than anywhere else in the world. And it has been there, quietly, all along, through every voyage ever made across that ocean. Through the old sailing ships and the trading routes, through the fishermen and the explorers and the ordinary boats crossing between ports. Through everyone who has ever looked out across that water and thought it looked exactly like any other sea. All of them passed over the deepest dent in Earth's gravity, and none of them ever knew. It waited. It made no sign. It was simply there, this enormous gentle absence, this 100-meter bowl of missing sea spread across 3 million square kilometres, holding its silence beneath the keels of the world. There is something almost tender about that, I think, if you let yourself feel it in this drowsy hour. The idea that the biggest single feature of its kind on the whole planet could sit right there under everyone, in plain sight, on the open ocean, and stay completely hidden. Not because it was small, it is the opposite of small, but because it was too gentle, too spread out, too soft in its slope for any human sense to catch it. It hid not by being far away, but by being everywhere and nowhere at once, dissolved across an area so vast that no single glance could ever hold enough of it to notice the tilt. And this is the strangeness that our whole night rests on, that the largest gravitational dent on Earth is also one of the most perfectly invisible things on Earth, that you can stand at the very centre of it and be surrounded in every direction by more than 100 meters of missing sea and feel nothing and see nothing and have no way in your body to know it is there at all. Which brings us back gently to the question I set down earlier and left glowing in the hall like a small lamp. If this thing is invisible to the eye, if it is imperceptible to the body, if no sailor in all of history ever caught the faintest hint of it from the deck of a ship, then how did anyone ever find it? How do you go looking for a thing that gives itself away to none of your senses? How do you map the shape of a dent you cannot see, cannot feel, cannot measure with any tool you could carry in your 2 hands on a rolling deck? That is the puzzle. And the answer is one of the quietly astonishing stories in all of the sciences, and I am going to unfold it for you slowly across the hours ahead. Because the answer runs from a man sealed inside a submarine in the middle of the last century, watching a pendulum swing back and forth in the pressurized dark beneath the waves, trying to escape the endless rocking of the surface so that he could measure the pull of the earth cleanly for the first time. And it runs from there up into the sky, up past the clouds, and past the air itself, to a pair of satellites, twins, chasing each other around the planet in the cold vacuum of space, measuring nothing but the tiny changing distance between the two of them, a gap they can track to less than the width of a single human hair, and using that impossibly small measurement to weigh the entire world. And it runs to another spacecraft still, a strange arrow-shaped thing flying lower than any of its kind, so sleek that the people who built it called it the Ferrari of space, feeling out the faint gradients of gravity as it skimmed the very edge of the atmosphere. We will meet all of them. We will meet the pendulum in the submarine, and the twins in orbit, and the low-flying arrow, one by one, unhurried, and we will see how each of them, in its own way, learned to feel a dent that no eye could ever see. And once we have found the low, once we truly have it mapped and measured and understood as a shape, we will go looking for the harder thing. We will go looking for the reason. We will sink down past the ocean floor and through the flowing rock of the deep earth, down toward a boundary almost 3,000 kilometres below the waves, where molten metal presses against solid stone. And we will consider the leading idea of what is actually missing down there, and why gravity has grown so faint above it. And I will be honest with you when we get there, because the truth is that no one is entirely certain yet, and the not being certain is part of the quiet pleasure of it, not something to be afraid of. But all of that is for the long, slow hours ahead. For now, there is only this. There is a place in the Indian Ocean where the sea leans down more than 100 meters, across a bowl 3 million square kilometers wide, and where you would weigh the tiniest fraction less than you do right now, and where gravity itself has softened its grip on the world. And nothing about it is dangerous, and nothing about it is frightening, and no ship has ever come to harm there, and none ever will. It is simply the deepest dimple on the great gravity potato of the Earth, the truest low point in the sea level of gravity, a gentle, enormous absence that hid itself in plain sight for the whole of human history. And we are going to follow it down, you and I, all the way to the bottom, as slowly as sleep will allow. So stay with me, or drift off, if the drifting comes. Either one is exactly right. Let the shape of that invisible bowl float somewhere behind your eyes, vast and gentle and harmless. A place where the ocean quietly leans a little lower because the earth, in that one great patch of blue, is pulling just a little more softly than anywhere else in the world. And let me carry us, from here, back to a cold grey stretch of sea more than 70 years ago, and to a man who first went looking for the pull of the earth from inside the belly of a submarine, because the ordinary ships on the surface would not stop swaying long enough for him to feel it. His name was Felix Andries Vening Meinesz, and he was a Dutch geophysicist, and in the years after the First World War he had found himself with a problem that most scientists of his era had simply decided to set aside and wait on, because the problem seemed, on its face, almost deliberately intractable. He wanted to measure the pull of gravity over the ocean. This sounds, if you let the words settle into you slowly, like a reasonable enough ambition. Gravity is a thing that pulls, and the ocean is a vast and available surface, and surely one might take one's instruments to a ship and make one's readings in the usual way. But anyone who had ever tried it understood, fairly quickly, why the ocean was not cooperative. A ship at sea moves. It rolls with the swell, it pitches in the wind, and even in relatively calm weather, on a fine clear morning with the water behaving itself, a ship is never entirely still. It is always describing small arcs and tilts and wobbles, rising and falling on the slow breath of the water beneath it. And those movements, however small they seem to a person standing on the deck, are enormous to a precision instrument trying to feel a gravitational signal that is, at its most interesting, a fraction of the Earth's total pull. The particular instrument Vening Meinesz relied on was a pendulum. The pendulum has been humanity's gravity meter for a long time, because the rate at which a pendulum swings, the tick and tock of its arc from one side to the other, depends directly on the strength of the gravitational pull beneath it. A stronger pull swings the pendulum faster. A weaker pull lets it slow. So if you set a very precise pendulum in a very stable environment and count its oscillations with great care, you can read gravity from it, the way a musician reads tempo from a metronome. The trouble is that the ship's rolling and pitching adds its own accelerations to the pendulum, and those accelerations are large and chaotic and very difficult to separate from the quiet, steady signal of the Earth's pull below. Vening Meinesz had a solution, and the solution was to go underwater. Below the surface, a few meters down, the rolling of waves becomes something much smaller. A submarine, once it has descended even a short distance beneath the chop and the swell, moves in a world that is much, much calmer than the surface. The great long undulations of the sea that rock a ship from side to side become, down in the dark, something almost negligible. The water above acts as a kind of enormous patient damper, absorbing the chaos at the surface and returning stillness to whatever lies beneath. And Vening Meinesz had reasoned, correctly, that if he could get his pendulum apparatus into a submarine and take it down below the waves, he might be able to make the measurements that surface ships would never allow him to make cleanly. It was not a comfortable solution. Submarines in the mid-20th century were loud, cramped, smelling of diesel and machinery and the particular close heat of too many people in too small a space. They were built for other purposes entirely. But Vening Meinesz was a patient man, and he made his arrangements, and he brought his pendulum apparatus aboard and found a place for it, and he went to sea in the belly of a metal tube beneath the waves. And he measured. He measured in the North Atlantic and in the Pacific and in the waters around Indonesia, and he mapped, piece by careful piece, the way gravity varied across the ocean floor in ways that no one had seen before. And by 1948, as he continued to refine his data and extend his surveys across the Indian Ocean, his measurements were beginning to outline something that would take decades more to fully understand. A broad, deep softening in the pull of the Earth in the region south of the Indian subcontinent, a place where gravity was measurably, genuinely, undeniably quieter than it should have been. He could not see the full shape of it. No single pendulum, measured from no single submarine, could give you the three-dimensional map of something so vast. What he had was more like a sketch, a first suggestion, a series of readings that said, plainly, that something here is different. The Earth is not pulling as hard in this direction. There is, somewhere beneath these waves, an absence. But that sketch was enough to set the question into the record, and the question, once set, would not leave. It would sit there quietly for the next several decades while the science slowly gathered the tools it would need to answer it properly. The tools, when they came, were not pendulums in submarines. They were satellites, moving through the dark above the atmosphere at speeds that no ship and no submarine could approach, and they would transform the vague outline Vening Meinesz had drawn into something precise and detailed and strange beyond anything he might have imagined from the deck of his cramped research vessel. The leap from a man in a submarine with a pendulum to a pair of satellites measuring their own separation to a fraction of the width of a human hair is not a small leap. It is one of the great quiet leaps in the history of human measurement, the kind that happens slowly enough that no single moment marks it clearly. The kind where you look back from one side and then from the other and realize that something fundamental about what we can know and how we can know it has changed entirely. Satellite geodesy, the science of measuring the shape and gravity field of the Earth from orbit, grew steadily through the second half of the 20th century. The earliest satellites, beginning in the late 1950s, gave geodesists something new and strange and enormously useful. An object moving in space whose orbit depended directly on the gravity field below it. A satellite in a perfectly uniform gravity field would trace a perfect ellipse around a perfectly smooth planet, regular and repeating, the mathematics of it clean and simple. But the Earth's gravity field is not uniform. It is lumpy, uneven, stronger in some places and weaker in others, and a satellite responding to all of that unevenness will trace an orbit that wobbles and shifts in subtle ways, pulled slightly ahead here and slightly back there by the varying mass distribution below. And if you can track a satellite's orbit precisely enough, you can work backward from the wobbles to reconstruct something of the gravity field that caused them. This was the principle, and the early satellites gave geodesists their first global view of the broad-scale features of the gravity field, including a confirmation that yes, in the vicinity of the Indian Ocean south of the subcontinent, there was something genuinely unusual. Not just a local quirk in a single set of readings, but a real, globe-spanning anomaly that showed up in the orbits of satellites that had never been anywhere near India, because the gravity they were responding to below them was the Earth's entire field, felt all the way from orbit. But understanding the rough shape of something and mapping it precisely are very different things, and the mapping of the Indian Ocean Geoid Low in the precise, detailed form that the scientists of the 21st century would come to work with required a mission more sophisticated than anything the early satellite era could provide. It required GRACE. GRACE stands for Gravity Recovery and Climate Experiment. It was a joint mission between NASA, the American Space Agency, and the German Aerospace Center, known by its German initials as DILA, along with the German Research Center for Geosciences, GEFS, and it launched in 2002, not as a single satellite but as a pair, two spacecraft flying in formation in the same orbit, separated by a distance of roughly 220 kilometers, one following the other around the Earth at an altitude of several hundred kilometers, circling the globe again and again, day after day, for years. The two satellites were given names. Informally, the scientists and engineers who worked with them called them Tom and Jerry, after the cartoon characters, because the arrangement of one chasing the other around the planet at the same relentless orbital pace struck someone, at some point, as having something of the quality of that perpetual cartoon pursuit. One always ahead, one always behind. Neither ever quite catching the other, circling forever. But what Tom and Jerry were doing as they circled was not running. They were listening to gravity. Here is how the measurement works, and it is worth settling into slowly, because the ingenuity of it is the kind of thing that, once you understand it, stays with you as a small, quiet marvel. As the two satellites orbit the Earth, they are continuously measuring the distance between themselves, the precise gap from the nose of the trailing satellite to the tail of the leading one, across 220 kilometres of open space. They do this with a microwave ranging system, sending signals back and forth between them, and using the timing of those signals to calculate the separation. And the precision of that measurement is extraordinary. The system can detect changes in the separation between Tom and Jerry of less than a micron, less, that is, than 1/1,000,000th of a metre, less than the width of a human hair, which is typically somewhere around 50 to 100 microns across. The satellites can feel each other growing closer or farther apart by an amount that you could not see, could not feel, could not measure with any instrument you might hold in your hands, and yet the microwave system between them registers it cleanly. Now think about what that means when the leading satellite, Jerry say, passes over a region where there is a concentration of mass beneath the surface of the Earth. A buried mountain range, say, or a dense geological formation, or a region where the mantle is particularly heavy and compact. That mass pulls on the satellite as it approaches. It pulls it very slightly forward in its orbit, accelerating it just a little, giving it a small additional boost that the pure orbital mechanics alone would not predict. And so the leading satellite speeds up almost imperceptibly, and the gap between it and the trailing satellite increases. Tom and Jerry move apart. Then, as the leading satellite passes over the dense region and the trailing satellite approaches it, the trailing one feels the same gravitational boost and accelerates as well, and the separation closes again. And after both satellites have passed over the feature, the trailing satellite is now being pulled forward while the leading one has moved past, and so the gap continues to change, responding to the geography of mass beneath them in a continuous flowing record that captures the gravity field below with exquisite detail. This is the inverse of what seems intuitive. You might imagine that measuring gravity from space requires looking downward, a sensitive detector aimed at the Earth, reading the pull. But Grace does not look down. Grace looks at itself. The two satellites measure each other, the distance between them, and from the way that distance breathes and shifts across millions of orbital measurements. Spread across years and years of flying, the scientists reconstruct the gravity field that caused those breathings and shiftings. It is as though you wanted to map an invisible landscape, and instead of trying to photograph it, you released two balls to roll across it, and then recorded in perfect detail how they moved relative to each other, and from that record alone you rebuilt the terrain. And because the system is measuring not a force but a distance, not the pull of gravity, but its effect on the separation between two known objects, it can achieve a sensitivity that no conventional gravimeter carried on an aircraft or a ship could match. The mountains and valleys of gravity that Vening Meinesz had glimpsed from inside his submarine with a swinging pendulum, Grace could see from 400 kilometres up, in 3 dimensions, month by month, year by year, watching not only the static pattern of dense and light regions deep in the Earth, but also the way that pattern changes over time as water shifts between the land and the sea, as ice sheets melt or grow, as the invisible slow breathing of the planet's interior goes quietly on. The Indian Ocean Geoid Low appeared in Grace's data with a clarity that the older methods had never achieved. Not as a vague softening in a set of submarine readings, not as a slight wobble in a satellite orbit noticed and noted and filed away, but as a precise, detailed, three-dimensional portrait of an enormous bowl in the gravity field. The kind of portrait that lets scientists not just say yes, the low is there, but say exactly where it is, exactly how deep it goes, exactly what its edges look like, exactly how its depth varies across its expanse. The full shape of the deepest dimple on the gravity potato of the Earth, laid out in a map that Vening Meinesz, watching his pendulum swing in the belly of a submarine in 1948. Could not have imagined, and would, one suspects, have found quietly astonishing. But Grace was not alone. There was another instrument, measuring the same field by a different method, and it deserves its own moment in this slow account because it is one of the more elegant pieces of engineering the space age has produced. The European Space Agency launched a mission called Ghosh in 2009. Ghosh stands for Gravity Field and Steady-State Ocean Circulation Explorer, and the people who built it gave it a nickname, the Ferrari of Space. The nickname came from its appearance. Where most Earth observation satellites look roughly like boxy, functional contraptions covered in solar panels at odd angles, Ghosh had a streamlined, aerodynamic shape, tapered, arrow-like, with fins and a smooth, angular body designed not to look elegant, but to deal with a genuine engineering problem that was particular to the science Ghosh was trying to do. The problem was altitude. The lower you fly a satellite, the stronger and more detailed the gravity signal you can detect. Gravity weakens with distance. So being closer to the surface means being closer to the mass features you are trying to map, and closer means more sensitive. But the lower you fly, the thicker the atmosphere you are moving through, even if the atmosphere at 400 kilometres altitude is vanishingly thin by any earthly standard. And as Ghosh needed to fly very low, around 255 kilometres, significantly lower than most satellites, it would experience a constant, very slight drag from the trace atmosphere remaining at that altitude, and that drag would constantly slow the spacecraft and introduce perturbations in its motion that would contaminate the gravity measurements. The fins helped, the aerodynamic shape helped, and Ghosh also carried electric ion thrusters that fired continuously and very gently, maintaining the satellite's speed against the drag so that it always flew at a constant rate, never slowing, never perturbed by the thin whisper of air above the atmosphere. The thrusters were like an invisible hand, perpetually pushing back against the resistance, so that the spacecraft's motion was governed only by gravity and never by the messy friction of residual air. And inside Ghosh, at its core, was a gradiometer, a device that measured not the pull of gravity at a single point, but the difference in gravitational pull across a very small distance. 6 ultra-sensitive accelerometers arranged in pairs along 3 perpendicular axes, each pair separated by about 50 centimeters, measuring the differential gravity, the gradient, across that short span. If you are 50 centimeters closer to a buried mass concentration than your neighbor, the gravity you feel is very slightly stronger than what your neighbor feels, and the difference between those two measurements is the gravity gradient. And from thousands upon thousands of these gradient measurements, taken continuously as Ghosh flew its low passes over every part of the globe, scientists could reconstruct the fine-scale structure of the gravity field with a sharpness that the Grace microwave system, operating at its much longer baseline but much higher altitude, complemented rather than duplicated. Grace and Ghosh together were like two very different instruments playing the same composition from different registers. Grace, with its long baseline between twin satellites, was sensitive to the large-scale, slowly varying features of the field, the broad continental scale anomalies, the deep, long wavelength signals from the mantle far below. Ghosh, with its ultra-precise gradients measured at low altitude, captured the finer, shorter wavelength features, smaller scale density contrasts in the crust and upper mantle, structures that Grace's longer baseline tended to smooth over. Together they gave geodesists something that neither could provide alone: a map of the gravity field that was both deep and sharp, both broad and detailed. The most precise description of the planet's gravity that had ever been assembled. Ghosh flew until 2013, when it ran out of the xenon fuel that fed its ion thrusters. Without the thrusters to maintain its altitude against the drag of the high atmosphere, the spacecraft began to slow and descend, and within weeks it re-entered the atmosphere and burned. The Ferrari of space ended as a streak of light across the sky, a brief brightness that lasted only seconds before it was gone. It had spent 4 years measuring the gravity field at finer resolution than anything that came before, and it had left behind a legacy of data that scientists would work through for years after the satellite itself had ceased to exist. Grace, the original Tom and Jerry, continued past its projected 5-year lifespan by a decade, operating until 2017, far longer than the engineers who designed it had planned or even firmly hoped. 15 years of measuring the separation between two satellites to within a fraction of a human hair's width. 15 years of watching the gravity field breathe with the seasons and the ice and the slow shifts of water mass across the continents. 15 years of adding to the record of the planet's changing self. And then it, too, was done. But the measurements did not stop. In 2018, Grace Follow-On launched, sometimes called Grace FO, carrying the same microwave ranging system as its predecessor and carrying also something new, an experimental laser ranging interferometer. Where Grace measured the separation between its twin satellites using microwaves, Grace FO's laser system used the much shorter wavelength of laser light to make the same measurement with even greater precision. Light oscillates at a far higher frequency than microwaves, and higher frequency means finer resolution in the ranging measurement. Means the ability to detect even smaller shifts in the distance between the satellites, means sensitivity to gravity signals that were previously below the threshold of detection. The laser system on Grace FO is an experiment, a technology demonstration, a step toward a future in which the measurement of the Earth's gravity field from orbit becomes finer still, more precise still, more revealing still. And so the watch continues, the chain that Vening Meinesz began in 1948 from his submarine, measuring the swing of a pendulum to feel the pull of the Earth in a patch of Indian Ocean, extends now into the orbit of paired satellites, measuring their own mutual distance with lasers, building a map of gravity that he could not have conceived of, serving a science he helped begin. It is worth pausing here, in this slow account, to consider what all of that measurement added up to. What it added up to was this, the full, precise portrait of the Indian Ocean Geoid Low. Not a suggestion, not a wobble in a set of readings to be noted and tentatively interpreted and revisited later. A map. A detailed, three-dimensional, quantified description of a bowl in the gravity field of the Earth, centred roughly south of the Indian subcontinent, near the southern tip of India and Sri Lanka, with a maximum depth measured relative to the smooth, idealized reference ellipsoid, the average smooth Earth shape that geodesists use as their baseline, of about 106 meters. 106 meters. The gravity surface, the geoid, sits 106 meters below where it would sit if the Earth were a smooth, uniformly dense sphere rotating quietly on its axis. In the single deepest point of the low, the sea level of gravity sags by more than the height of a 30-story building below the level a smooth Earth would predict. And that sag is not a hole. It is not a cliff or a crevasse or a void. It is a bowl, a gentle, gradual depression spread across 3 million square kilometres of ocean, its edges sloping so slowly and over such enormous distances that from any point within it the surface of the water looks flat and ordinary, the horizon sits at the usual distance, the waves behave in the usual way, and there is nothing, no visual clue. No physical sensation, no instrument that a navigator on a ship would think to consult, that would tell you were at the bottom of the deepest dimple in the gravity field of the entire planet. The sea does sit lower there. It genuinely does. The water, responding to the weaker pull of gravity in that region, sits further from the centre of the Earth than it would if gravity were stronger. Meaning the sea surface in the middle of the low is perhaps 80 or 90 meters lower in absolute terms than the sea surface in a region of strong gravity like the Western Pacific or the waters near Iceland. But 80 or 90 meters spread over 3 million square kilometers is a slope so gentle, so gradual, that it would take a very long time even to walk from one end of it to the other. And the drop in height would be imperceptible at any scale a human body could measure directly. Ships cross the Indian Ocean Geoid Low every day, and have for all of human maritime history, and not one of them has ever been swallowed by it, or drawn toward a centre, or spun into some kind of oceanic drain. Because there is no drain, and no centre in any physical sense that would affect a ship. And the waters of the low are open and deep and ordinary and entirely safe, and the only thing unusual about them is something that no human eye can see and no human body can feel, the very slightly softer grip of the earth below. There is a small and satisfying footnote to all of this. One of those quiet places where the deep science of the planet's shape turns out to touch the ordinary tools of everyday life. When you look at your phone and ask it how high above sea level you are standing, and the phone considers for a moment and gives you a number, 10 meters or 50 or 240, that answer depends on a geoid model. It depends on a mathematical description of the lumpy, uneven gravity surface of the Earth, the true sea level that accounts for all the variations in mass below the surface, the wobbles and sags and bulges of the geoid potato. The height your phone gives you is not the height above the smooth reference ellipsoid, the idealized mathematical Earth, but the height above the actual geoid, the surface that water would take if it covered everything and listened only to gravity. And that geoid, that number your phone uses quietly in the background without ever mentioning it, was built from data. Satellite data. Grace data. Ghosh data. Years and years of measurements made by satellites measuring their own separations to within a fraction of a hair's width, or measuring gravity gradients across 50 centimeters of space inside a sleek arrow-shaped spacecraft burning xenon to hold its altitude. The Indian Ocean Geoid Low is part of that model. That 106-metre dip south of India is folded into the mathematics that your phone uses when it tells you your altitude. The deepest dimple in the gravity potato of the Earth is, in a small and entirely hidden way, part of the infrastructure of modern navigation. part of the invisible architecture of the maps and measurements that the world runs on, corrected for and accounted for and built into the systems that we carry in our pockets and consult without a second thought. It is one of the things that tends to become quietly remarkable when you follow it far enough. The way that the most remote and abstract-seeming science, the measurement of gravity variations across the deep ocean, measured from satellites hundreds of kilometres above the surface, tracing their origins to the composition of the mantle thousands of kilometres below. The way that science, when you follow its threads long enough, turns out to be quietly present in the ordinary world, baked into the answers your phone gives you on a Tuesday morning, built into the maps that navigate the ships, supporting the measurements that build the buildings and plot the courses and establish the coordinates of the daily world, none of which you would know by looking at it. The low keeps its secrets by wearing the face of ordinary blue ocean. The geoid model keeps its secrets inside algorithms you will never read. The satellites keep their secrets in data archives that most people will never know exist. But the connections are there for anyone who follows the chain far enough. And this too is part of the pleasure of it, the way the hidden and the everyday turn out, in the end, to be the same thing, seen from different distances. But knowing that the bowl exists, and knowing its shape in extraordinary detail, and knowing even that your phone is quietly correcting for it, none of that answers the deeper question. None of that tells you why the bowl is there at all. None of that tells you what is missing far below the waves to make gravity sag in that great broad softening south of India, across all those millions of square kilometres of quietly unremarkable sea. For that, you have to go down. You have to follow the gravity signal not upward into orbit, but downward into the Earth, through the ocean floor and the crust beneath it, down through the mantle, the vast, slow-moving interior of the planet, down toward the boundary where solid rock meets molten iron, where the temperatures climb to numbers that feel almost geological in their abstraction. You have to understand something about what the deep Earth is made of, and how it moves, and why the movement matters, and why the word movement itself requires a particular kind of patience to apply to rock that, in a human lifetime, goes nowhere you could measure. The satellites told us where the bowl is. They told us its shape and its depth with a precision that would have seemed miraculous to the man in the submarine watching his pendulum in 1948. But the satellites, for all their elegance, for all the years they spent measuring each other across the dark, cannot tell us the source. The source is hidden deeper than any satellite can reach, deeper than any direct measurement can go. To find it, you need a different kind of listening, and that is what we will turn to now, as the hour grows late, and the air in the room grows still, and the slow account of this strange invisible bowl continues its long descent. Think of gravity, for a moment, as a kind of weight scale, except the scale is the Earth itself, and what it weighs is everything inside it. Every cubic metre of rock, every pocket of dense iron, every tendril of lighter material rising slowly through the mantle, all of it registers, all of it contributes its small fraction to the total gravitational pull you feel if you happen to be standing above it, or orbiting above it in a pair of satellites chasing each other across the dark. Gravity, in this sense, is not mysterious. It is arithmetic. It is mass and distance, and nothing else, the most honest accounting the planet makes. It does not keep secrets. It cannot hide what is inside it. Every excess of mass pulls the surface of the sea slightly higher, and every deficit lets the sea surface sag slightly lower, and that sagging, that gentle dimpling of an otherwise featureless ocean, is a direct confession. The planet is telling you, with all the subtlety of water finding its own level, exactly what it contains and where it contains it, and where, deep down below the floor of the Indian Ocean, in a column of material stretching for hundreds and then thousands of kilometres below the waves, something is lighter than it ought to be. This is what the satellites measured. Not the rocks themselves, not the flowing material in the depths. They measured the result, the consequence, written on the surface of the sea in a difference of 106 metres, spread so gently across 3 million square kilometres that no ship ever felt it. But what produced that result? What lies in that column of lighter than expected material stretching from the floor of the ocean down into the slow interior of the planet? That is a different question, and answering it requires following the signal downward into a part of the earth that no instrument has ever directly touched, that no drill has ever reached, that no human hand will ever hold. The understanding of it has been built up the way you might understand the arrangement of furniture in a completely dark room. Not by walking into it and touching the chairs and tables, but by listening to the way sound travels through the space, the way it bounces and slows and changes pitch depending on what it meets, and assembling from all of those reflections and delays a picture that you trust not because you have seen it, but because the picture, built from many different kinds of listening at once, consistently makes sense. Start at the beginning. Start with what is actually down there. Below the floor of the Indian Ocean, below the thin, cold crust of oceanic basalt that covers it. The earth is mostly mantle. The mantle is a vast, thick layer of rock, silicate rock, the same general family of material you might find in the walls of a mountain or the boulders in a river, though under pressures and temperatures that bear no resemblance to anything on the surface. It extends from just below the crust, a handful of kilometres down, all the way to roughly 2,900 kilometres below your feet. 2,900 kilometres. To put that in terms that might make it feel real, the distance from the coast of England to the coast of eastern Canada is roughly 5,000 kilometres. The mantle is more than half that distance thick, and it is, in every sense that matters, on a human timescale, solid rock. You could not push your hand into it. You could not flow through it. At the pressures and temperatures of the deep mantle, rock behaves like the most obstinate, most unyielding thing imaginable. And yet it moves. Not quickly. Not in any way that a human lifetime or 10 human lifetimes would let you observe. But the mantle moves, slowly, over timescales measured in millions of years, in the same way that a jar of very thick honey moves if you leave it tipped on its side for long enough. Scientists call this solid-state creep, which is a technical way of saying that even solid rock, given enough time and enough heat from below and enough pressure from above, will flow. Hot material rises. Cooler material sinks. The mantle convects, moves in slow, enormous, planet-spanning loops, material ascending near some regions and descending near others. Driven by the temperature difference between a very hot core below and a much cooler surface above, exactly as warm air rises from a radiator and cool air sinks from a ceiling, except that the material doing the rising and sinking is rock, and it is doing it at a speed of roughly a few centimetres per year. A few centimetres per year. About as fast as your fingernail grows. About as fast as the continents drift apart. And this slow convection, this barely perceptible creep of rock on geologic timescales, is the engine of nearly everything dramatic that happens on the surface of the planet. The shifting of the continents, the building of mountain ranges, the opening and closing of ocean basins, the folding of rock into landscapes that take human breath away. It is also, in a very direct sense, the engine of the gravity dent that the satellites mapped from orbit. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. But before you can understand the engine, you need to understand the floor of the engine room. At the very base of the mantle, 2,900 kilometres below the surface of the sea, there is a boundary. It is called the core-mantle boundary, and it is, in the vocabulary of planetary science, a remarkable place. On one side of it, below, is the outer core, liquid iron and nickel, moving and churning and generating the magnetic field that surrounds and protects the Earth. On the other side, above, is the solid silicate rock of the deepest mantle. And the contrast between these two materials, at that boundary, is greater than almost any other contrast anywhere inside the planet. Greater, in terms of density, than the contrast between the rock of the surface and the open air above it. On one side, molten metal, enormously dense, white-hot at temperatures somewhere between 3,700 and 4,000 degrees Celsius or more, pressing upward with the energy of a core that has been radiating heat since the planet formed. On the other side, solid rock, cooler by comparison, pressing down with the weight of everything above it. The boundary between them is not gradual, it is sharp, geologically speaking, and strange, and it is a place where the dynamics of the whole planet play out in slow motion. If you wanted an image for it, think of the very bottom of a pot of water set to simmer on a stove. The pot itself is the core-mantle boundary. Below the pot is the heat source, the burner, the core, and the water above the pot is the mantle. Except that the pot in this case is not metal, and the water is not water, and the timescales involved mean that what you would see as vigorous bubbling in a kitchen takes hundreds of millions of years in the interior of the Earth. The physics, though, the hot material rising from a heated boundary, the cooler material descending, is recognizably the same. Heat rises, density falls, the convection turns. And it is at this boundary, or just above it, that some of the most dramatic and least understood structures in the entire planet sit. They were found by sound. Not the ordinary sound of the surface world, not the sound of voices or wind or rain, but seismic waves, the sound the earth makes when it shakes. When an earthquake occurs, it sends waves of energy radiating outward through the planet in every direction, and those waves travel at speeds that depend, precisely and predictably, on what they travel through. Dense, cold rock transmits seismic waves quickly. Hot, less dense material slows them down. And so, by placing seismometers all over the surface of the Earth and recording the timing of waves arriving from distant earthquakes, some of them having passed all the way through the interior on their journey, geophysicists can reconstruct, with growing resolution, what the inside of the planet looks like. Not in colour, not in visible form, but as a map of where waves move fast and where they move slow, which translates directly into a map of where rock is cold and dense and where it is hot and lighter. This technique is called seismic tomography, and the name is deliberately borrowed from medical tomography. The same logical structure as a CT scan of the human body, except that the scanner is the Earth itself and the signals are earthquakes. What seismic tomography found over decades of refinement and with data collected from thousands of earthquakes by instruments on every continent and the floor of the sea is that the mantle is not uniform. It is not a smooth, homogeneous body of slowly convecting rock. It is instead a richly structured place, full of fast and slow regions, of rising columns and descending sheets, of ancient material that has been cycling through the interior for so long that it carries the fingerprints of oceans and continents that no longer exist at the surface. And at the very base of the mantle, sitting atop the core-mantle boundary, the tomographic maps revealed two enormous structures that looked like nothing anyone had expected to find. Two regions, each roughly the size of a continent. Some comparisons reach for the word Africa to give them scale, and Africa is not a small frame of reference where seismic waves slowed down dramatically, more than anywhere else in the deep mantle. Two great, irregular, continent-sized masses of material sitting at the very bottom of the solid Earth, in the zone just above the molten iron of the outer core, and apparently very different in their physical properties from the mantle rock surrounding them. Scientists call them the large low-shear velocity provinces. The name is precise and technical and does not quite convey the strangeness of the things it names. In the literature they are sometimes called, more plainly, the blobs. One of them sits below the African continent and the South Atlantic Ocean. The other sits below the Pacific Ocean. Each one rises from the core-mantle boundary upward into the mantle for somewhere in the range of hundreds of kilometres, perhaps approaching 1,000 kilometres in height, depending on the model and the method, and each one spreads laterally across the base of the mantle for distances that dwarf anything at the surface. They have been sitting there, in all likelihood, for hundreds of millions of years, possibly longer. They may be remnants of the early Earth, dense exotic material that never fully mixed with the rest of the mantle. Or they may be the accumulated residue of ancient subducted slabs that sank and pooled at the base of the mantle over geologic time. The precise nature of what they are made of is one of the most actively studied and contested questions in deep earth science. What is clear is that they are large, that they are different from the surrounding mantle, and that they appear to influence what happens in the mantle above them, including, according to the study from Bangalore that we will come to, what happens in the Indian Ocean. The African blob, in particular, sits in a position that places it in the geological neighbourhood of the Indian Ocean and the region beneath it. The mantle is not a static medium. The blobs are not simply resting there passively, doing nothing. They appear to be the sources, or at least the deep anchors, of structures that rise upward from the core-mantle boundary toward the surface. Rising columns of hot, less dense material called mantle plumes. Think of the blob as a slow-burning campfire at the very base of the mantle, and the plumes as the columns of warmer air that rise from it. Except that the campfire here is a continent-sized anomaly of hot exotic rock, and the rising columns are fingers of warmer, lighter mantle material ascending toward the surface over millions of years, driven by the temperature and density contrast between themselves and the cooler, denser mantle rock surrounding them. Plumes of this kind are thought to produce, at the surface, the geological features called hotspots, places where a persistent source of heat from the deep mantle burns through the moving surface plates above it. The Hawaiian island chain is the classic example. As the Pacific plate has moved northwest over millions of years, a stationary deep hotspot has punched through it repeatedly, leaving a trail of volcanic islands stretching across the ocean. Iceland is another, where the plume beneath it has been adding material to the surface for millions of years, keeping Iceland volcanically alive long after you would expect a patch of ocean floor at a mid-ocean ridge to have gone cold and sunk. These surface expressions are where the idea of mantle plumes first gained traction. There are places on Earth where the ordinary rules of how volcanism and tectonics work together cannot explain what is being produced, and deep, persistent plumes rising from the base of the mantle offer an explanation. But plumes are not always visible so neatly at the surface. Sometimes they rise into a region where the dynamics of the overlying plate, or the thickness or composition of the lithosphere above, suppress or diffuse whatever surface expression they might otherwise produce. And sometimes the effect of a plume on the gravity field above it is more significant, more measurable, and more revealing than any surface volcanic expression. The density of a rising plume column, lighter, hotter material ascending through cooler, denser surroundings, is itself a gravitational signal. Light material means less mass. Less mass means weaker gravity. Weaker gravity means the geoid sags. And a plume, or a collection of rising low-density material of sufficient size and duration, operating at sufficient depth across a large enough region of the mantle beneath the Indian Ocean, would produce exactly the kind of broad, deep, persistent negative gravity anomaly that the satellites have mapped. That is the chain of reasoning. But before you can fully follow it, you need one more piece. The piece that explains not just what is rising beneath the Indian Ocean, but what is simultaneously, and in a deep sense causally, sinking. The mantle, in its convective cycle, does not only have material rising. For every column of material ascending from the hot base, there is, somewhere else, material descending, cooler, denser rock, sinking back down under its own weight, completing the loop. And the most dramatic, most clearly imaged form of sinking material in the mantle is not just any rock. It is the preserved remnants of ancient ocean floors. When tectonic plates collide, when a plate carrying dense oceanic crust meets a plate carrying lighter continental crust, the oceanic plate loses. It subducts. It bends downward and plunges beneath the lighter continental plate, sinking into the mantle below. This is how ocean floors are consumed, a process as old as plate tectonics itself, continuous, planet-spanning, and deeply important to the chemistry and structure of the mantle. The Pacific Ocean floor is being consumed around its edges right now, at the Cascadia subduction zone off the coast of Oregon and Washington, at the Japan Trench, at the Mariana Trench. The process is ongoing. It has been ongoing for hundreds of millions of years, and the material it produces, the cold, dense slabs of ancient oceanic crust descending into the mantle, can be tracked by seismic tomography, because cold, dense rock transmits seismic waves faster than the surrounding mantle, and the slabs show up as bright, fast wave regions threading downward through the tomographic maps. What happens to a slab once it starts to sink depends on how deep it gets. Near the surface, in the upper mantle, slabs descend relatively straightforwardly, though they can be deflected and complicated by the dynamics of the trench and the surrounding mantle. At a depth of roughly 660 kilometres, there is a transition, a boundary zone in the mantle where the pressure is high enough to force the minerals of the sinking rock to reorganize into denser, more compact crystal structures. This transition zone acts in some circumstances as a kind of barrier or speed bump. Some slabs stall there, spreading out horizontally along the boundary, pooling into wide, flat accumulations of cold, dense material, before eventually continuing their descent. Others punch through more directly, carrying their cold, dense cargo into the lower mantle below. The ones that make it through the transition zone and continue sinking can travel very deep indeed. Seismic tomography, as its resolution has improved decade by decade, has revealed structures that appear to be ancient slab material sitting at extraordinary depths, in some cases reaching all the way to the core, mantle boundary itself, nearly 3,000 kilometres down, where the slab material accumulates in what geophysicists sometimes call slab graveyards. The term is evocative. The image it suggests is accurate. Ancient ocean floors, long since removed from the surface of the earth by the relentless process of subduction, gradually descending through the whole depth of the mantle over hundreds of millions of years and coming to rest at last at the very bottom, against the molten iron of the outer core. Cold, dense, inert at the scale of a human life, but contributing their density to the base of the mantle, and, if the models are right, interacting with the hot material near the core, mantle boundary in ways that send consequences rippling back upward. The thing about the mantle is that its convective cycle is not one-directional. Sinking slabs do not simply accumulate without consequence. They displace the material around them. They disturb the thermal structure of the region they enter. Cold material arriving at the base of the mantle in one place, pooling against the core, mantle boundary, pushes warmer material sideways. It creates pressure differences. It can, in the right circumstances, push lighter, hotter material upward elsewhere, triggering or reinforcing, or redirecting the rising plumes that seismologists and geodynamicists have been studying for decades. The mantle is not a set of independent vertical pipes, some going up and some going down, unaware of each other. It is a single interconnected convective system, and what happens in one part of it eventually sends a signal to every other part, though the signal may take millions of years to travel. This interconnection, the way that a sinking slab on one side of a regional system can eventually drive a rising plume somewhere else, is central to what the 2023 study from the Indian Institute of Science proposed for the Indian Ocean Geoid Low, and to understand what the Bangalore team found in their simulations. You need to know which slabs they were thinking about, and why those particular slabs had both the location and the history to produce the kind of deep mantle disturbance that could carve a dent in gravity and hold it open, gently, for millions of years. The answer begins with a vanished ocean. An ocean so thoroughly erased from the surface of the earth that the only evidence of its former existence is the rock that once formed its floor, now sinking through the mantle, and the gap it left in the gravity field above the sea that replaced it. The ocean was called the Tethys, and to understand what it was and what became of it, it helps to hold in mind a picture of the world as it was, not as it is, to let the present-day map of the earth dissolve and be replaced by something older and stranger and harder to orient yourself inside. Several 100 million years ago, the configuration of the continents was profoundly different from the one on any map you have ever used. The land masses that are now India, Antarctica, Australia, South America, and Africa were assembled into a single enormous supercontinent in the southern hemisphere called Gondwana. And between Gondwana and the landmasses to the north, the predecessors of Asia and Europe, there was an ocean. a broad, warm, shallow sea that has left its fossils in the mountains of the Alps and the Himalayas and the Middle East, in limestone beds that were once seafloor and are now thousands of meters above sea level. That ancient sea is the Tethys Ocean. Its name comes from a sea goddess of Greek mythology, chosen by the Austrian geologist Eduard Suess in the 19th century when he first recognized the evidence for a lost ocean in the rocks of Europe and Asia. The Tethys was a real ocean. It had a floor of oceanic crust, the same dark basaltic rock that covers the floors of the Pacific and Atlantic today. It had seafloor spreading at its center and subduction at its margins, the whole tectonic machinery of an ocean basin operating for hundreds of millions of years. And then, over a very long time, tens of millions of years, it was consumed. As the continents reorganized themselves, as the fragment that would become India broke away from Gondwana and began drifting northward across the ancient ocean, the Tethys floor was subducted ahead of it. The oceanic crust of the Tethys descended into the mantle at the margins of the approaching continents, consumed kilometre by kilometre, as India moved north, as Africa moved north, as the great southern landmasses gradually closed the gap between themselves and the Eurasian landmass to the north. India's journey northward is one of the more dramatic events in the recent, and in geological terms, relatively recent, history of the planet. It moved at a speed that, by the standards of plate tectonics, was remarkable, fast enough to close an ocean and build a mountain range in what amounts to a geologically brief window of time. The collision of the Indian plate with the Eurasian plate, somewhere around 50 to 60 million years ago, crumpled the rocks at the boundary zone into what became the Himalayan mountain range, the tallest on Earth. Still rising as India continues its slow push northward today. But ahead of that collision, for the tens of millions of years that the approach lasted, the floor of the Tethys was being steadily subducted and consumed, the oceanic crust of a whole ocean, bending downward at the margins and sinking into the mantle, cold and dense and carrying with it the record of everything that had once been the floor of that warm ancient sea. Those subducted slabs, the remnants of the Tethys Ocean floor, are what seismic tomography has found in the mantle beneath the Indian Ocean and surrounding region, in images that show fast wave material, cold and dense, threading downward through the interior. They have been sinking for tens of millions of years. The oldest portions of them may have reached extraordinary depths by now, may have accumulated at or near the core-mantle boundary, the cold graveyards of a sea that vanished from the surface of the earth long before our species existed, long before mammals existed, long before the dinosaurs had come and gone. And it is what those sinking Tethyan slabs did to the mantle around them. The material they displaced, the convective currents they stirred and redirected, the hot, low-density material they pushed aside and upward, that the scientists in Bangalore proposed as the mechanism behind the gravity dent that the satellites have so precisely mapped. The ghost of a dead ocean, sinking, the echoes of its descent, rising, and between those two slow movements, separated by the depth of the whole mantle, the signal writing itself on the surface of the sea in a gentle, invisible 100-metre bowl. But we are getting ahead of the story, because between the fact of the sinking slabs and the proposed mechanism of the rising plumes and the gravity dent they create, there is a gap, a significant, honest, important gap that the science is still working to close. The simulations from the Indian Institute of Science are elegant and carefully constructed. They reproduce a low of the right shape and depth in the right location. They provide a coherent chain of cause and effect, from the Tethys floor sinking through the mantle to the low-density plumes rising beneath the Indian Ocean to the mass deficit that makes gravity sag. But a simulation is not an observation. A model that reproduces something is not the same as direct evidence that the mechanism it proposes is the actual mechanism at work in the real Earth. And the deep mantle, for all the power of seismic tomography, for all the elegance of the gravity maps from Grace and Ghosh, for all the sophistication of the convection models, remains a place we have never directly seen. The plumes that the model requires, those rising columns of hot, low-density material beneath the Indian Ocean, driven upward by the displacement caused by the sinking Tethyan slabs, have not been unambiguously imaged in the seismic tomographic maps. The model needs them to be there. The gravity signal is consistent with them being there. But the seismic evidence for their precise structure, their extent, their connection to the African large low-shear velocity province below is not yet the kind of clear, independent confirmation that would close the argument. Other geophysicists have proposed explanations that do not require the same specific plume geometry, explanations that tie the gravity low more directly to the structure of the sinking slabs themselves, or to the broad thermal and compositional structure of the mantle in that region, without invoking the specific rising plume dynamics. The community broadly agrees that the Indian Ocean Geoid Low is a deep mantle phenomenon, that something about the density structure of the mantle hundreds and thousands of kilometres below the sea surface is producing the gravity deficit that the satellites measure. But the exact configuration of that density structure, which material is where, how it got there, what is driving what, remains a question with more than one serious answer. This is, if you allow it to be, a beautiful place for a story to rest. Not a failure of knowledge, not a baffling mystery in the sensational sense, but the honest and rather wonderful condition of science at the edge of what it can currently reach, where the tools have been refined to extraordinary precision, where the maps are as detailed as they have ever been, where the models are genuinely sophisticated and genuinely constrained by real data, and where the answer is close enough to feel almost within reach, but not yet close enough to hold in your hand with certainty. The deep mantle is one of the last truly difficult places on Earth. Not inaccessible in the way that a distant galaxy is inaccessible, the Earth is, after all, the rock we stand on, the planet we know the surface of better than any other. But inaccessible in a more fundamental way, the pressures and temperatures of the deep mantle are beyond any drill, any probe, any direct instrument. Everything we know about it has been learned indirectly, by listening to the waves that pass through it, by measuring the gravity it produces at the surface, by running simulations of how it ought to behave and comparing those simulations to the maps the measurements provide. What we have is a convergence of different kinds of evidence pointing in the same general direction toward an explanation that is coherent and grounded and genuinely illuminating about the deep history of the planet, while still carrying, honestly acknowledged, the caveats that any explanation built on inference and modelling must carry. The Tethys Ocean sank. The mantle was disturbed, something rose in response, and the rising of lighter material created a deficit of mass that gravity dutifully recorded and the sea surface dutifully responded to, sagging very gently, very broadly, very invisibly, across a region of ocean that no sailor has ever thought to measure with anything more sensitive than the rise and fall of the waves. And it was precisely that convergence, that quiet agreement between different instruments, different disciplines, different ways of listening to a planet that cannot speak directly, that made it possible in 2023 for a team of researchers in Bangalore to do something that had not been done before. Not to solve the mystery, which would be too strong a word for what they accomplished, but to construct a model of the deep earth that, for the first time, produced something that closely resembled the Indian Ocean Geoid Low, its shape, its depth, its position, without being told in advance to do so. The team worked at the Indian Institute of Science in Bangalore, which sits roughly above the Geoid Low itself. If you drew a vertical line from the Institute's buildings down through the crust and the mantle and into the deep rock below. Attreyee, Ghosh and Debanjan led the work, and what they published in geophysical research letters was not a new measurement of the low, and not a new satellite observation, and not a new map of the seismic velocities beneath the Indian Ocean. What they published was a simulation. A computer model of how the mantle ought to behave, given what we know about how it moves, how it carries heat, how it responds to the slow, inexorable sinking of cold, dense material, and the slow, inexorable rising of hot, light material over millions and tens of millions of years. Mantle convection models have existed for decades, and they are genuinely impressive things. Attempts to capture in mathematical form the behavior of a layer of solid rock that flows like a liquid when you wait long enough. Rock that creeps at speeds measured in centimeters per year, the speed of a growing fingernail, and yet moves with enough force and persistence to carry continents across the face of the planet and to drive the circulation of heat from the deep interior outward. You cannot run an experiment on the actual mantle. You cannot heat a rock to 3,000 degrees at pressures 100,000 times greater than the atmosphere and watch what happens over 10 million years in a laboratory. What you can do is write down the equations that govern how such a material ought to behave, the equations of viscous flow, of heat transport, of density and pressure and phase transitions at different depths, and solve those equations numerically on a computer, letting the virtual mantle run forward in time while you watch. What Ghosh, and their colleagues found when they ran their simulations was this: most configurations of the deep mantle did not produce a geoid low resembling the one we observe. The low they were trying to explain is not subtle. It is 106 meters deep. It is the deepest single dimple on the surface of gravity that exists anywhere on Earth. Whatever is causing it powerfully, and most reasonable arrangements of mantle density and flow simply did not produce anything like it in the right place. But when the model included plumes, columns of hot, low-density material rising through the mantle beneath the Indian Ocean region, something changed. The simulated geoid developed a depression, and as the plumes in the model were tuned to reasonable values, grounded in what we know about how plume material behaves, the simulated depression began to look, in its shape and its depth, like the real one. The model did not produce a perfect match, and the researchers were careful not to claim that it did. But it produced something recognizably similar in a way that earlier models without the rising plumes had not. The reason rising plumes would create a geoid low comes back to the central logic of gravity and mass. A plume is a column of material that is lighter than the surrounding rock, lighter because it is hotter, and hot rock expands and becomes less dense, the way warm air rises in a room because it weighs slightly less per unit volume than the cooler air around it. Where lighter material rises and displaces denser material, the total mass in that column of the mantle is reduced. And reduced mass means weaker gravity. And weaker gravity means the sea surface, which follows the geoid, sags downward. The geometry is invisible and the scale is enormous, but the logic is the same logic that governs why a balloon rises or why a piece of wood floats on water. Lighter things tend upward. Where they go, mass goes with them, but less of it, because they are lighter. And gravity notices. The question the model then raised, the question that gives the explanation its deepest and most haunting dimension, is where these rising plumes come from, and why they should be here, beneath the Indian Ocean, and not somewhere else. The answer the model pointed toward was the Tethys Ocean. The Tethys Ocean no longer exists. It has not existed in any form recognizable as an ocean for tens of millions of years. It was the great equatorial sea that separated the northern supercontinent of Laurasia from the southern supercontinent of Gondwana in the deep past of the planet, before the continents reached anything like their current arrangement. As those landmasses drifted and eventually the familiar shapes of the continents took form, the Tethys was slowly consumed, its oceanic floor subducted, carried downward at the margins where plates converged, drawn into the mantle by the density of old, cold oceanic crust. And the Indian plate, as it drifted northward over tens of millions of years, drove that consumption. The Indian plate is one of the great movers of the last 100 million years or so of Earth history. It left the ancient southern supercontinent and moved north at rates fast by geological standards, covering the distance that now separates the Indian subcontinent from Antarctica in a geological eye blink. As it moved north, its leading edge drove into and beneath the oceanic floor of the Tethys. And the Tethys floor was pushed down, subducted, and slowly drawn into the mantle. And eventually, roughly 50 to 55 million years ago, the Indian plate's northward movement brought it into direct collision with the Eurasian plate, and that collision, still ongoing, still lifting the Himalaya upward at rates of a few millimeters per year, was the final chapter of the Tethys. There was no longer an ocean to consume. The plates had met. But the slabs of Tethyan oceanic crust that had already been subducted did not simply vanish. Subducted slabs are cold and dense, far denser than the surrounding mantle into which they sink, and they carry their density with them as they descend. Seismic tomography, the technique of using earthquake waves as an X-ray of the deep earth, watching how waves speed up through cold dense rock and slow down through hot light rock, has revealed that subducted slabs can be tracked as fast wave anomalies sinking through the mantle, sometimes pausing or stalling at the major transition zone at around 660 kilometers depth, and sometimes plunging through that transition and continuing downward toward the base of the mantle, toward the core-mantle boundary, nearly 3,000 kilometers below the surface. In the scenario proposed by the IISC team's model, this is what the Tethyan slabs did. They sank. Cold and dense, they continued downward through the mantle over millions of years, and as they descended, they displaced the material around them, pushing aside the rock of the lower mantle, rearranging the deep interior, and in doing so, helping to drive a return flow of lighter, hotter material upward. The deep mantle, disturbed by the long descent of cold slabs, responded by pushing plumes of lighter material upward in regions adjacent to where the slabs were sinking. And those rising plumes ascending beneath the Indian Ocean reduced the mass in that column of mantle, weakened the gravity above them, and drew the sea surface slowly, invisibly, gently, downward. There is something almost poetic in the sequence if you hold it still for a moment. An ocean that disappeared millions of years ago, its floor swallowed by the movements of plates whose edges have since collided and locked, continues to shape the world above. The Tethys is gone. Its water has long since been redistributed into the global ocean. Its coastlines are now mountain ranges or ocean floors or ancient sedimentary rock buried beneath younger deposits. But the weight of its floor, cold and dense and still descending in the deep mantle, still reaches upward through the chain of cause and effect, still touches the surface of the sea in the very broad and very gentle form of 106 meters of missing gravity. The low is, in the interpretation the IISc model suggests, a kind of afterimage, a memory of a lost ocean, written not in stone where anyone could read it, but in the curvature of the sea surface, in the very slightly weaker pull of gravity over a patch of water 3 million square kilometres wide. The model also gave the low a rough age. The simulations suggested that the geoid low, specifically a low of the depth and character that we observe today, had not always been there. The conditions that created it, in the model's telling, developed over time, and the low as it exists now formed within roughly the last 20 million years. 20 million years is a long time by any human measure. It is long enough for species to evolve and go extinct, long enough for river systems to carve deep canyons, long enough for coastlines to change shape entirely. But in the time scale of the deep earth, 20 million years is recent. The mantle convects on timescales of hundreds of millions of years. The continents have been moving for billions of years. The formation of the geoid low within the last 20 million years, only after the Tethyan slabs had descended deep enough into the lower mantle to stir the dynamics that drove the plumes, makes it, in geological terms, a young feature. A recent development. Something that was not there when the dinosaurs went extinct 66 million years ago. Something that formed in what the planet would consider the recent past, and it connects, in the model's picture, to one of the deepest and most discussed structures in all of deep Earth geophysics, the large low-shear velocity provinces, the continent-sized regions of anomalously slow seismic waves that sit at the very base of the mantle, just above the core-mantle boundary. Roughly 2,900 kilometres below the surface. There are two of them. One sits beneath Africa, one sits beneath the Pacific. They are enormous, each one roughly the size of a continent, each one rising hundreds of kilometres upward from the core-mantle boundary, each one a region where seismic waves travel more slowly than they do through the surrounding deep mantle, which tells us that the material there is different in some way, possibly hotter, possibly chemically distinct, possibly both. Geophysicists call them, informally, the blobs. The African blob, the large low-shear velocity province beneath Africa, is implicated in the IIS model's picture as part of the deep source region whose dynamics helped feed and sustain the rising plumes beneath the Indian Ocean. The connection is indirect, mediated by the slow circulation of the deep mantle over millions of years. But it runs from one of the most ancient and mysterious structures at the base of the mantle to the surface of the Indian Ocean, where the sea surface records the result in the language of geometry. A bowl that is 106 meters deep and completely invisible to the eye. This is where the story arrives at its most important caveat, and the caveat deserves to be stated clearly and held there for a moment, because it is not a footnote and it is not a hedge for the sake of politeness. It is an honest description of where the science stands. The plumes the IISc model requires, the specific columns of rising low-density material that the simulation places beneath the Indian Ocean, have not been directly imaged. Seismic tomography has revealed the large-scale structure of the mantle with impressive resolution. And it has found the blobs, and it has found evidence of cold sinking slabs in various places. And it has found regions of slower than expected seismic velocities in many places that may represent hot material. But the specific plume structures that the Ghosh and Powell model relies on have not yet been independently confirmed by seismic images with enough resolution and clarity to count as direct evidence. The model produces plumes that match the gravity observation. The gravity observation confirms that something is producing a mass deficit in the right place. But the chain of inference between those two facts, the claim that the mass deficit is specifically caused by plumes of the type the model describes, driven by the Tethyan slabs in the way the model proposes, rests on the model's self-consistency and its ability to reproduce the observation. That is genuinely strong evidence. It is not the same as seeing the plumes directly. Alternative explanations have also been proposed, and they deserve acknowledgement. Earlier work, and some competing interpretations, tied the geoid low not to rising plumes, but more directly to the subducted slabs themselves, and to broader patterns of mantle density variation. Without requiring the specific upwelling geometry the IISC model introduces. These explanations are not wrong in their basic premise. They too recognize that the low is a deep mantle phenomenon, a consequence of the density structure of the mantle below, but they place the primary cause in different configurations of material. The community of researchers who study the deep mantle broadly agrees that the Indian Ocean Geoid Low is a signal from far below, from the mantle, from the long history of plate tectonics and subduction and the slow circulation of the interior. The disagreement is in the geometry, in which specific arrangement of sinking dense material and rising light material best accounts for the observation. And that disagreement is not close to being settled, because no single instrument sees the cause directly. This is the fundamental challenge of deep Earth science, and it is worth sitting with. The gravity map, produced by Grace and Ghosh, tells us the low exists and describes its shape precisely. The seismic tomography tells us something about the density structure of the mantle. Reading the planet through earthquake waves the way a doctor reads a body through ultrasound. The plate motion history tells us what has happened at the surface, the Tethys consumed, the Indian plate's collision with Eurasia, the rise of the Himalaya. The convection models try to weave these threads together into a coherent story about the deep interior. But none of them, individually, is a photograph of a plume. None of them provides the kind of direct evidence that would end the discussion. What they provide instead is a convergence of plausible inference. The kind of convergence that science often produces when direct observation is impossible, when the thing you want to understand is too deep, too hot, too slow, too large, or too remote for any instrument to touch. In those situations, the best science can do is listen carefully from a distance through multiple different channels and look for a story that fits all of them. And for the Indian Ocean Geoid Low, the story that currently fits best, the one that has the most explanatory power, the most mathematical support, the most coherence with what we know from seismology and plate history, is the story the IISC model told. The Tethys sank, the mantle stirred, something rose, and gravity sagged. It is an explanation that is genuinely illuminating, even if it is not yet final. And illuminating is the word not in the sense of a bright light that removes all shadow, but in the sense of a candle held up in a large dark room, casting enough light to see the shape of things nearby, while leaving the far corners still in darkness. Let the darkness be comfortable for a moment. Let the shape of what is known rest there, neither exaggerated nor diminished. There is a place in the Indian Ocean where the sea surface sits 106 meters lower than it would if gravity were perfectly uniform across the planet. The sea surface does not look lower there. There is no cliff, no rim, no visible edge. A ship crosses that region of ocean, and the crew notices nothing unusual. The horizon is where the horizon always is. The waves are the waves they always are. The depth of the water beneath the keel is the depth it would be anywhere else in the Indian Ocean. The sage is not in the water. It is in the shape of gravity itself, in the curvature of the equipotential surface that oceanographers call the geoid, the surface that the ocean follows not because of its own shape, but because of the invisible pull of mass distributed unevenly in the planet far below. A Dutch geophysicist first sensed the edges of this bowl in 1948, sealed inside a submarine with a pendulum. Taking measurements that would not make sense until satellite missions decades later gave them their full context. And the satellites, Grace, with its twin craft chasing each other in orbit and measuring the distance between them to a fraction of the width of a human hair, Ghosh flying lower than most satellites dare. Reading the gradient of gravity with accelerometers of extraordinary sensitivity, Grace follow on, carrying its laser interferometer into orbit to continue the record. Turned that sensed absence into a precise and detailed map. A map of missing mass, written in the language of gravity, stretching across roughly 3 million square kilometres of ocean south of the Indian subcontinent. And that map, read alongside the seismic maps of the deep mantle and the plate motion history of the last 100 million years, pointed toward an explanation that is both geologically specific and quietly astonishing. A vanished ocean, its floor still sinking, and in response to the sinking, something lighter rising in its place, reducing the mass in a column of mantle that now runs from the sea surface down nearly 3,000 kilometres to the boundary with the molten iron of the outer core. A mass deficit produced by displacement, recorded at the surface as a dimple in the geoid, a bowl in the sea surface that is real and measurable and completely invisible. The planet is doing this constantly. Everywhere beneath the surface, in every region of the mantle, the slow convection continues, cold material descending, hot material rising. The interior redistributing its heat over timescales so long that the human mind can hold the numbers without truly grasping them. The Indian Ocean Geoid Low is one of the loudest signals that convection produces in the language of gravity. But it is not the only one. Gravity anomalies exist across the entire geoid surface, the Potsdam potato, with its highs and its lows. Its +85 meters near New Guinea and its 106 meters south of India is a map of every density variation in the planet, every region of cold dense slab and hot light plume and ancient chemically distinct reservoir, all of them reaching upward through the gravity field and touching the surface with a signature that, if you know how to read it, tells you something about what is happening 2,000 kilometers down. This is what the phrase means, gravity quietly betraying the churning deep inside. Not betrayal in the sense of treachery, betrayal in the older sense, the sense of revelation, of something hidden becoming visible. The deep mantle cannot be drilled, cannot be sampled, cannot be visited by any probe, but it cannot hide entirely, because its mass speaks. Every density variation, every degree of temperature difference, every pocket of lighter or heavier material produces a gravitational signature that propagates upward through the rock at the speed of the gravitational field, instantly, in physical terms, and touches the surface. The geoid is, in this sense, a portrait of the deep interior. Imprecise, blurred by the distance and by the complexity of the layers between surface and source, but real. The lumpiness of the planet's gravity is the lumpiness of its interior, projected upward onto the surface of the sea. And the tools we have built to read that portrait have grown more sensitive with each generation. From a pendulum swinging inside a submarine to twin satellites measuring their own separation with microwave ranging, from microwave ranging to a laser interferometer reading the distance between the satellites with the precision of light itself. Each improvement in measurement has revealed finer detail in the gravity map, more structure in the portrait of the interior. And the portrait is not static. Grace and its successors have also shown that the gravity field changes over time, as ice sheets melt, as groundwater is pumped from aquifers, as the slow redistribution of mass at the surface shifts the geoid month by month and year by year. The static geoid that records the Indian Ocean Low is a long-term signal, driven by deep processes. But sitting on top of it, season by season, is the restless signal of the surface, water moving, ice moving, the planet's shallow skin in constant rearrangement. Somewhere in those overlapping signals, the deep one, from the mantle and its ancient inheritance from the Tethys and the sinking slabs, and the shallow ones, from the changing distribution of water and ice at the surface, lies a picture of the Earth that no previous generation of humans has been able to see. Not because the planet has changed, but because the instruments have grown patient enough to listen. The patience required is immense. Grace launched in 2002 and far outlasted its intended 5-year life, continuing to measure until 2017, 15 years of the satellites chasing each other in their low orbit, the distance between them shifting in response to every mass variation below, the data accumulating into a record of the planet's gravity field that grows more valuable with each passing year. Ghosh flew from 2009 until 2013, when its xenon propellant ran out and it began to descend, its orbit decaying slowly until it re-entered the atmosphere and burned. The Ferrari of space, ending as a brief streak of light somewhere over the ocean, its work complete. Grace follow-on carries the record forward, its laser interferometer, a refinement that the engineers of the original Grace could only dream of when they launched their twin craft in 2002. And from those measurements, from the patient accumulation of data across years and decades, the picture of the Indian Ocean Geoid Low has become as detailed as any gravity feature on Earth. Its edges are mapped, its depth is known. Its shape is constrained well enough that any proposed explanation must reproduce it faithfully in order to be taken seriously. The 2023 model from the Indian Institute of Science took that constraint seriously. It reproduced the low. It offered an explanation that is coherent and physically plausible and connected to the documented history of the Tethys and the Indian plate, and it left open, honestly, the questions that have not yet been answered, the questions about the specific geometry of the plumes, the questions about how much the deep blobs are involved, the questions that future seismic tomography, with ever finer resolution, might eventually address. Those questions are not a failure of the science, they are the frontier. The place where the known meets the not yet known, where the methods are real and the evidence is real and the answer is not yet fully visible. Every field of science has a frontier, and the frontier of deep earth geophysics is, in many ways, one of the most honest frontiers there is. Honest because the practitioners know very clearly what they do not know, and they say so, and they continue building better instruments and better models and waiting for the planet to tell them more. If you could stand on that frontier, not literally, because it is 2,000 kilometres underground and unreachable by any means, but imaginatively, the way it is possible to stand imaginatively at the edge of anything vast and strange, what you would find there is not a wall and not an emptiness, but something more like a question written in the rock, in the gravity, in the slow circulation of material that has been moving since the planet formed. The question is not fully legible, but it is legible enough to know what it is asking. It is asking, in the language of density and temperature and the curvature of the sea surface, what happened to the Tethys, and where did it go, and what did the going leave behind? And the answer, so far as the answer has been assembled, is this: the Tethys went into the mantle, cold and dense, and sank toward the core, and in sinking it pushed lighter material upward, and the lighter material rising in the mantle beneath the Indian Ocean created a deficit of mass, and the deficit of mass weakened gravity, and the weakened gravity let the sea surface sag, very gently, very broadly by 106 meters across a bowl of ocean that no sailor has ever seen and no diver could ever reach the bottom of, because the bottom is not the ocean floor. The bottom is the gravity field itself, which has no bottom that any instrument we possess can touch directly. What remains, when all of that has been said, is something that feels less like a solved problem and more like a map with the center filled in and the edges still fading into uncertainty. The center is real. The Indian Ocean Geoid Low is real. The satellite measurements are real. The connection to the deep mantle is real. The proposed connection to the Tethys Ocean and its sinking slabs is real as a model, real as a hypothesis, real as the best current answer to a question the planet is asking in a language we have only recently learned to read. What the edges hold is still being worked out, and that working out will continue for as long as people continue to launch satellites and run models and press their instruments against the faint signals the deep Earth produces. There is something in that continuity that is worth noticing on the way to sleep. The signals were there before the instruments. The Indian Ocean Geoid Low existed before anyone knew to look for it, before Felix Andries Vening Meinesz sealed himself inside a submarine with a pendulum in 1948, before anyone thought to put twin satellites in orbit and measure the distance between them to a fraction of the width of a human hair. The geoid was always that shape. The sea surface always sagged there. The Tethys slabs were always sinking, and the mantle was always responding, and the gravity field was always recording the result. The only thing that changed over the decades and the satellite missions and the modelling studies was the listening. The planet was always speaking. We simply grew quiet enough and built instruments sensitive enough to begin to hear. And what we heard was this: beneath one of the world's great oceans, in a region of water that looks exactly like all the other regions of water that surround it, the ground of gravity itself is more than 100 meters lower than it ought to be, because something vast and slow is happening far below. A ghost ocean sinking, light rock rising, the interior of the planet in its endless slow rearrangement, writing the story of its own past in the only language available to it, the language of mass and distance and the invisible pull that holds everything together. If you are still here, still listening, still following this slow descent into the deep earth, tell me where in the world you are right now. Wherever it is you have come to rest tonight. The window between you and the geoid low may be a few thousand kilometers, or it may be the width of an ocean, but the pull of the planet reaches everywhere equally, and the same gravity that shaped that invisible bowl in the Indian Ocean holds you gently where you are, against the surface of a world that is still, in its depths, quietly in motion. There are more stories here of this same slow and careful kind, waiting for whenever you want them. You have done enough for one day. The Tethys can keep sinking without you tonight, and the mantle can keep its slow, patient circulation, and the satellites can keep measuring the distance between themselves to the width of a fraction of a hair, and none of it requires your attention until morning. History will still be here in the morning. For now, rest.